Assalamualaikum warahmatullahi wabarakatuh. We are from group 2. We'll explain about lab report of the fluid friction. We are from section M01 and this is the name and ID of our members. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iqbal Afid bin Shamsuddin and my method number is MA19031. For the introduction, the flow of fluid in the pipe follows a certain governing equation. They are among them will follow the continuity equation where it states that the mass of fluid entering the pipe will be equal to the mass of liquid coming out of the pipe. It also follows the equation of energy as well as others. Viscous fluids are known as Newtonian fluids. This fluid will become viscous when it flows. This causes the flow of the lamina or in some other cases to be turbulent. Viscosity can also produce friction, which has the effect of reducing the amount of energy in the fluid flow. The purpose of the experiment is to observe and understand the nature of the frictional flow of fluids in pipes and their contact with fluid's Reynolds number. This experiment is carried out to show fluid friction, determine components of major losses in pipe system, and to investigate minor losses influenced by special pipe components and fittings. When fluid flows through a pipe, the frictional energy that occurs on the surface of the pipe will be converted into heat or sound energy. This energy loss is referred to as head loss obtained using the Bernoulli principle. Head loss can be classified as large head loss or small head loss. Small head loss is energy loss due to frictions such as bends and valves found in the system, and large head loss is energy loss due to frictional resistance acting against fluid flow. The objective of this experiment is to explain the mechanics of fluid friction phenomenon in pipes, understand and apply basic knowledge of major losses in straight pipes, and understand and apply basic knowledge of minor losses in pipe bends with various elbow values.
Assalamualaikum. My name is Rajana Razura MA19061. Now I'm going to explain about the theory of this experiment. Okay, in this experiment, the head loss due to friction can be calculated from the Darcy-Weisbach equation. Okay, where as shown here, this is the equation Darcy-Weisbach. Okay, where HL is head loss due to flow resistance, F is Darcy-Weisbach coefficient, L is pipe length, D is pipe diameter, V average velocity, and G indicate for gravitational acceleration. Okay, and then Reynolds number is given by this formula. Okay, the next is F can be determined by this equation, which is F equal to 0.3164 multiply with R Reynolds number to the power of negative 0.25.
Assalamualaikum and good day. My name is Daniel Bewan Abdullah and my number ID is MA19057. So today I will present about the chapter 3, which is method and procedure. For the 3.1 experiment setup, the fluid friction apparatus experimental unit is set up with the trim above the volumetric tank. The rear star and the nuts for pressure gauge mounting were unscrewed. The pressure gauge down was moved down one hole and the star and the nuts were tight again. Hose connection was set up between the hydraulic bench and unit. Make sure the main valve is closed before the fluid friction apparatus string is opened. The pump was switched on, then slowly open the main valve. Pressure gauge was connected to the desired measuring points. Ball coop was opened slowly. The feed and drain valve on the pressure gauge were adjusted to get the specific water level. The volumetric flow can be determined by stopping the time required to fill the volumetric tank from 10 to 20 or 30 liters. The drain valve below the tank was closed. The drain valve was open when the volumetric tank was full. And the last but not least, the pipe cannot run when dry. And for the equipment and material, we have to which is fluid friction apparatus and hydraulic bench. For the 3.3, which is experiment procedure, for the procedure for pipe flow friction factor, the appropriate section of the fluid flow apparatus was used, which is section A. The fluid friction apparatus was set up as figure 1. The dual pressure gauge was set up for the appropriate vertical and height. Seven different variations of fluid flow are altered to provide seven measurements of volumetric fluid and head loss while the pump is running. Measurements of volumetry and head loss were recorded. And for the experiment 2, of pi elbow loss coefficient and equivalent length, the appropriate section of the fluid flow apparatus was used in the experiment, which is section B. The fluid filtration apparatus was set up as figure 1. The dual pressure gauge was set up for appropriate vertical and height. The pump was set up in order to set the volumetric flow at the maximum value. The dual pressure gauge was tested at the first set of elbow, which is the pi elbow. The head loss value across the pi elbow was recorded. Step 5 and 6 were repeated for the pi bend and the pi angle 45 degree.
Hi, good day everyone. My name is Vijing San. I'm here to talk about the chapter 4 results, graph and discussion. And my ID is MA19054. So this is the result, 4.1 results. In this experiment, we divided into the experiment 1 and experiment 2. Experiment 1 is a pipe flow friction factor for the straight pipe. So this is the data obtained from the experiment. So this is the sample calculation. We are given with the parameters with the length, PVC pipe internal pipe diameter, PVC pipe thickness, and the water density, and water viscosity, of course, with the gravity. And then the formula that we apply in this experiment 1. So this is the sample calculation. We got the velocity, Reynolds number, and the friction factor, and of course the head loss. So this is the result after we tabulate all the data for the friction flow speed, Reynolds numbers, Blasius pipe friction factor calculated, head loss can measure head loss for the straight pipe. So this is the graph with the measure and the calculated head vs the volumetric flow. And this is the experimental, which is the pipe elbow loss for coefficient and equivalent length for the elbow pipe 90 degree, bend pipe 90 degree, and bend pipe 45 degree. So this is a volumetric flow for each of the pipe, which is all the same because using the same volumetric flow, but the head loss for the pipe is different. Elbow pipe, bend pipe, and the bend pipe 45 degree is different. So this is a sample calculation. Of course, this is the experiment we also use in the experiment, and then we calculate for the K and the loss coefficient and the equivalent length. So this is the tabulated data from the elbow pipe 90 degree, and this is for the bend pipe 90 degree and bend pipe 45 degree. So we tabulate all the data and with the loss coefficient, equivalent length in the last two rows, which is the calculated one, and then we compare using the graph. So you can see from here is the light blue one is the elbow pipe 90 degree, blue orange is the bend pipe 90 degree, and the gray one is the 45 degree. So this is the graph for the loss coefficient vs volumetric flow graph. And then we get the last graph is the equivalent length vs the volumetric flow graph. Also same. The blue one is the elbow pipe 90 degree, orange one is the bend pipe 90 degree, and gray one is 45 degree. That's all from me. Thank you.
Question 1, Experiment 1. What conclusion can be made from the head loss and the flow speed?
I will answer question 1. We can see from the equation itself that the head loss is directly proportional to the velocity of the fluid. Hence, from the experiment, we can deduce that as the speed of the fluid increases, the head loss will also increase as well.
Question 2, Experiment 1. What will happen to head loss if the length of the pipes is increased?
The length of the pipe is directly proportional to the head loss. Consequently, the head loss will significantly increase when the length of the pipe is increased. I will ask the next question. What would happen to the head loss if the diameter of the pipe is increased?
Hi, it's me again. My name is Vijing San, and I'm here to talk about the answer to the question 3 for the experiment 1. Clearly from the formula, we could indeed comprehend that the head loss is inversely proportional to the diameter of the pipe. For such reason, the head loss will drop significantly when the diameter of the pipe increases. Hi, my name is Vijing San, and it's me again. I'm here to question about the question 1 for the experiment 2. what is that relationship between flow speed and head loss?
Answer for question 1 is from the result obtained from the experiment, we recognize that as the flow speed is increased, the head loss will keep increasing too. This can further by certainly proved by the formula of the loss coefficient, which is k equal to tg as loss over velocity square. Shifting the velocity of the flow speed to the left is notable that the head loss is directly proportional to the flow speed. So I would like to ask the question for question 2. What is the connection between the elbow and bends in terms of its turning radius, head loss and loss coefficient?
Okay, the answer of the question is the head loss for the bend pipe of 45 degree at the lowest volumetric flow does have the highest value, followed by the elbow pipe of 90 degree and the bend pipe of 90 degree. Whereas at the highest volumetric flow, the head loss is higher than that of the head loss in an elbow pipe at 90 degree, but also lower than the bend pipe at 90 degree. For the loss coefficient, at the lowest volumetric flow, the bend pipe of 45 degree still has the highest value, followed by the elbow pipe of 90 degree and the bend pipe of 90 degree. Whilst at the highest volumetric flow, the head loss is higher than the head loss in an elbow pipe at 90 degree and lower than the bend pipe of 90 degree. So the last question for experiment 2 is what is the conclusion can be made considering elbow and bends in terms of its turning radius and equivalent length?
Answer 3, experiment 2. The conclusion that can be drawn considering elbows and bends, a relation of their turning radius and equivalent length will be that the bend pipe of 45 degree at the lowest volumetric flow has the highest value, followed by the elbow pipe of 90 degree and the bend pipe of 90 degree. Furthermore, at the highest volumetric flow, the equivalent length is greater than the equivalent length in an elbow pipe at 90 degree and lower than the bend pipe at 90 degree.